It was the height of the Cold War, the specific year 1959, when the clandestine architects of Lockheed's Skunk Works were handed a mandate that defied not just the enemy, but the very constraints of matter. The goal was simple, yet cosmically demanding: to build a reconnaissance machine that could not be intercepted, a vehicle that would travel at speeds where air itself became a hostile, abrasive medium. This pursuit of invulnerability required reaching Mach 3.2, a velocity that introduced a central ironic paradox, for the only thing fast enough to defeat a Soviet surface-to-air missile was the corrosive, blinding heat generated by atmospheric friction. What emerged, the sleek, almost terrifying outline of the Lockheed SR-71 Blackbird, was justly hailed as the ultimate aerodynamic achievement. Yet its true victory was not of form, but of chemistry, a logistical commitment to a petroleum product so exotic, so entirely outside the conventional boundaries of aviation, that it necessitated the complete rejection of every established rule of flight and maintenance. To cruise at an operational ceiling of 93,000 feet, the airframe would face kinetic temperatures exceeding 850 degrees Fahrenheit, turning the leading edges of the wings into glowing, shimmering thermal radiators, demonstrating that the enemy was no longer just the MiG, but the breakdown of molecular bonds, the inevitable deformation of aluminum. The physics were unforgiving. Mach 3.2, a speed that moved faster than the shadow of sound, demanded an entirely new understanding of materials science and, crucially, thermal management. Standard jet fuel, a commodity refined for conventional flight, would have turned to useless crystalline coke inside the Pratt & Whitney J-58 turboramjets within minutes, fouling the delicate combustion chambers and seizing the turbines. Worse, the high skin temperatures would have flash vaporized any conventional fuel, potentially turning the aircraft into a massive, uncontrolled thermal event. The solution, forged in the secrecy of the petroleum labs, was a bespoke chemical creature, the specialized JP7 fuel, a substance designed not merely to combust, but to defy combustion and to reject the thermal stress that crippled everything else. The supreme irony of this substance, the very lifeblood of the world's fastest machine, was its profound, stubborn inertness at ambient temperatures. JP7 possessed a flash point so extraordinarily high that igniting it required a volatile, hypergolic kick, the injection of a fiercely reactive chemical compound to simply begin the process of combustion. On the ground, this highly refined hydrocarbon elixir, essential for surviving the atmospheric inferno of Mach 3, was so thermally stable it posed virtually no fire risk. Yet, in a perfect encapsulation of the Blackbird's operational contradiction, the legends persisted of JP7 dripping from the thermally stressed panels of a cooling airframe and melting the asphalt on the runways below. This humble, mundane chemical reaction, the dissolution of a petroleum byproduct by a petroleum product, became the ultimate undeniable symbol of a machine that, even when motionless, existed in a state of chemical and thermal reality utterly separate from the conventional world of flight. It was a fuel designed to operate only when the atmosphere tried to destroy the machine holding it, and in that contradiction lay the foundation of America's technical and logistical supremacy. The earliest flights, those secretive leaps toward the edge of the atmosphere in the developmental A-12 program, were not triumphs of speed, but agonizing laboratories of material failure, relentless collisions between human ambition and the non-negotiable laws of thermodynamics. Engineers at the Skunk Works, fueled by that distinctly American hot rod mentality, sought to push boundaries, but the atmosphere simply refused to yield. Bolts sheared, seals vaporized, and conventional aluminum structures warped like cheap tin in the sustained thermal assault. It was a relentless, expensive education in the humility imposed by high Mach numbers, forcing the realization that the design of the SR-71 could not be about mere speed, but about calculated, engineered survival in an environment engineered to destroy. The transition from the A-12, with its early, painful lessons, to the definitive Blackbird was the recognition that the airframe itself had to operate as a heat engine, demanding a wholesale rejection of traditional aircraft fabrication. This led to the revolutionary commitment to titanium alloy, an extraordinarily difficult and costly material to mill, weld, and maintain, comprising fully 93% of the Blackbird structure. Yet, even this robust, heat-tolerant metal could not defeat the thermal environment alone. It could only survive it through ingenious, counterintuitive design. The iconic black skin of the aircraft was not a continuous sheet of metal, but a mosaic of panels designed with a precision that mocked conventional tolerances. On the cool, dark tarmac, the seams gaped visibly, allowing the infamous, persistent weep of fuel that defined the Blackbird's static presence. This was not a flaw, but a feature, a necessary calculated allowance for the thermal expansion that occurred as the aircraft approached Mach 3.2, a speed at which the skin temperature climbed toward the critical 850 degrees Fahrenheit. Only at that blistering speed would the airframe swell and the panels lock into place, sealing the machine and making it truly aerodynamic and structurally sound, a machine designed to be structurally imperfect until it achieved its mission speed. Yet this thermal strategy, the reliance on titanium and calculated gaps, only mitigated the external heat. The internal systems, the crucial hydraulics, avionics, and flight controls, still had to be protected from the colossal friction-induced temperatures. This is where the specialized JP-7 fuel transcended its primary role as propellant to become the aircraft's primary heat sink, its vital cold circulatory system, acting not as a combustion agent, but first and foremost as a coolant. The fuel was routed through a complex internal plumbing network, circulating around the engine nacelles, across the hydraulic lines, and behind the sensitive equipment bays, absorbing the searing thermal load that would otherwise cook the aircraft from the inside out. The Blackbird was therefore a flying chemical reaction, where its performance was utterly dependent on its own fuel supply, acting as the ultimate, necessary buffer against the tyranny of the thermals. The staggering logistical requirement was that the aircraft required this massive volume of fuel not just to fly, but to keep from tearing itself apart in the process, making the fuel burn rate a function of cooling demand as much as thrust demand. This required a precise, continuous monitoring of temperature gradients across dozens of critical points, a system of sensors and micromanaged valves that dictated the flow of JP-7 to prevent any single section of the titanium structure or any crucial hydraulic fluid from exceeding its failure point. The very structure of the Blackbird was a testament to the industrial supremacy thesis. It survived only by forcing a highly refined hydrocarbon product to perform a dual duty, consuming fuel in astronomical volume, not purely for power, but for cooling and chemical defense against the laws of physics that had tried relentlessly to ground the ambition of the American reconnaissance program forever. The chemical identity of JP-7 was the invisible architecture of the Blackbird's superiority, a silent testament to the fact that high Mach flight was ultimately a problem solved not by aerodynamics, but by molecular stability. It was a highly refined hydrocarbon blend, an oil so stripped of impurities and volatile components that its very structure was the antithesis of conventional petroleum products. The core engineering feat was its sheer, uncompromising stability, an ultra-low vapor pressure that ensured it would not boil off into a catastrophic vapor cloud at the soaring temperatures of the airframe, and an incredibly high flash point that was the aircraft's primary defense against thermal ignition. This was a fuel designed to be chemically inert when the airframe was glowing with frictional heat, protecting the Blackbird's electronic and hydraulic systems through its remarkable reluctance to change state or combust. This chemical purity placed it in stark rhetorical contrast to the standard fuels that powered the rest of the world's air forces. JP-4, or the later JP-8, were commodities, mass-produced petroleum designed for common logistics, and conventional engine efficiency, accepting a degree of thermal and chemical volatility as a necessary trade-off for volume and accessibility. JP7, however, was a bespoke chemical product, demanding a refinery process of exquisite difficulty with strict limits on sulfur and aromatic content to prevent coking at extreme engine temperatures. The difference in cost and refinement protocols was exponential, representing not just a higher quality product, but a completely different echelon of industrial commitment. This commitment led directly to the establishment of the central thesis of logistical supremacy. The Blackbird's operational life was not merely dependent on titanium and engineering genius, but on a specialized, limited supply chain that only the economic power of the United States could sustain. Only a scant few refineries across the globe possessed the capability to achieve the stringent purity standards and specialized additives required for the creation of JP7. This logistical constriction meant that every operational deployment of the SR-71 demanded the advance, careful placement of dedicated JP7 storage and handling facilities, transforming a simple refueling stop into a complex chemical and supply chain endeavor. The very difficulty of simply producing the fuel was a constant underlying factor in the machine's overall operational cost and deployment inflexibility. This chemical design, while brilliantly solving the problem of thermal defense, introduced its own profound and ultimately ironic trade-off. By making the main fuel supply so stable, so stubbornly resistant to ignition in a hot environment, the engineers created a problem at the opposite end of the spectrum: how to start the massive J-58 engines in the first place. The solution was a controlled descent into calculated instability. The requirement of tetraethylborane, or TEB, a complex, expensive organometallic compound used purely as an ignition fluid. TEB was a fiercely hypergolic substance, reacting instantaneously and violently with oxygen upon injection to create the initial necessary flame to kickstart the reluctant, inert JP7. The visual contrast was arresting: a small, critical tank of a volatile liquid so aggressive it had to be stored under pressurized nitrogen, ready to erupt into a green, instantaneous flash of flame, sitting in the heart of a machine powered by a main fuel so sluggish that it simply refused to ignite on its own. The entire technical solution was a testament to American engineering's willingness to embrace a minute point of extreme, concentrated volatility, a controlled, calculated instability, to unleash the massive, unchallengeable power of a chemically restrained giant, ensuring that the Blackbird's invulnerability was a paradox sustained by the finest achievements of the petrochemical industry. The scene unfolds over the icy, unforgiving expanse of the North Pole, a vast white canvas against which the drama of Cold War logistics played out in an unseen, calculated ballet. At 27,000 feet, under an indifferent frozen sun, the KC-135Q tanker drone lumbered, its silhouette the very picture of unglamorous utilitarian necessity. This was the Blackbird's lifeline, its utterly essential partner in the dark mathematics of reconnaissance, the prosaic vessel that carried the bespoke, precious chemical elixir of JP7. For all its terrifying, unchallengeable speed, for all the titanium armor and the Mach 3.2 invincibility, the Lockheed SR-71 was, paradoxically, a machine defined by its absolute dependency. It could fly for hours in the edge of space, a ghost untouchable by missile or pursuit, but it possessed a crippling weakness. It could not, by design, take off with the massive volume of fuel necessary for a full mission, nor could it safely land with a significant reserve. Its operational profile was a bell curve of resource management, a fragile negotiation with gravity and physics that mandated frequent, critical reunions with the unheralded tanker. This fundamental constraint was rooted in the extreme nature of its flight envelope. To achieve its mission speed, the Blackbird had to engage its full engine power at relatively lower altitudes, speeds, and temperatures, a regime where its fuel consumption soared exponentially. The drag was immense, the efficiency low, meaning a significant necessary portion of its fuel was devoured merely to climb to the altitude and velocity where it could then transition to the more efficient but still demanding ramjet-like engine cycle. Thus, the mission was a logistical palindrome, an immediate post-takeoff rendezvous for fuel, followed by the high Mach sprint, and then another, sometimes multiple, rendezvous for the return journey, transforming the high-speed independent sprint into a meticulously choreographed high-stakes relay. The true measure of its operational success lay not in the pilot's skill alone, but in the unwavering reliability of the boom operator in the cavernous cold rear of the tanker. The sheer volume of the exchange underscored this dependency, a statistical reveal of the industrial effort required to sustain the Blackbird's speed. The KC-135Q would transfer up to 80,000 pounds of JP-7 in a single, tense mating, a deluge of the specialized hydrocarbon necessary to complete the mission. This was no ordinary tanker. The critical Q designation was its rhetorical badge of honor, signifying that the aircraft had been fitted with unique, dedicated internal plumbing, pumps, and specialized filtering systems designed solely for the handling of JP-7, safeguarding the Blackbird's ultra-sensitive engines from any contamination. The standard tanker fleet was unfit for the task. Only the bespoke logistical apparatus could service the bespoke machine. The tension during this ritual was palpable, a moment of profound vulnerability where the ultimate expression of American speed had to slow, descend, and expose itself to the world while engaging in a precise, slow-motion mechanical maneuver. It was the moment where the machine's grand, solitary independence was utterly stripped away. As one veteran Blackbird pilot, his voice carrying the deep weight of countless high-altitude engagements, once described the feeling of dependency. You're closing in on this huge, vibrating silver thing at 27,000 feet, and the whole world is holding its breath. It's 120 feet of pure, black, screaming technology, trying to mate with a big, corpulent milk bottle, all because you're carrying a chemical that's too hot to handle and too precious to waste. It's unsettling. You're the fastest machine on Earth, but in that moment, you're just a very thirsty, very vulnerable extension of that boom. The moment of connection was the ultimate juxtaposition. The elegant, supersonic stealth craft reduced to a helpless extension of its unglamorous partner, utterly reliant on the industrial and chemical logistics chain that stretched back thousands of miles, all for a tank of the expensive, hyper-refined fluid that was both its defense and its most profound vulnerability. The Blackbird could fly higher and faster than anything else, but only if the tanker was there, waiting with its promised cargo of the specific petroleum product that made the tyranny of the thermals a temporary, survivable condition. The Blackbird's purpose was a stark philosophical repudiation of direct engagement, a dramatic shift in the geopolitical reality of the Cold War. It was a weapon designed not for combat, but for avoidance, a silent, screaming testimony to the premise that the ultimate defense lay not in armor or armament, but in unreachable velocity. The SR-71 was designed to render every Soviet interceptor, every surface-to-air missile site, and every high-level threat irrelevant by the simple, non-negotiable fact of its speed. Flying a surveillance route meant entering a constant high-stakes negotiation with physics, a race against the enemy's reaction time, a negotiation where the American machine won every time by crossing the finish line before the starting gun of the missile launch could be heard. It was not merely fast, it was a visible, tangible manifestation of American confidence in industrial and engineering superiority. A challenge hurled across the Iron Curtain, stating unequivocally that the ingenuity of titanium and petroleum chemistry could defeat any conventional military response. This supremacy, however, came tethered to a crippling and complex logistical burden, rooted entirely in the exotic nature of its operation. Deploying the Blackbird was never a simple matter of flying to a forward base and checking in. It was a technical deep dive into logistics, requiring the pre-positioning of specialized maintenance, crews, custom ground support equipment, and most critically, the massive dedicated stockpile of the bespoke JP-7 fuel. Every forward operating location became a specialized chemical storage facility, operating under extraordinary protocols to handle a fuel that required stringent purity and specialized handling, transforming the simple act of stationing the aircraft into a massive industrial commitment. The ability of the United States to sustain this intricate global network of chemical support was, in itself, as formidable a deterrent as the aircraft's speed. The supreme irony of inertia defined the Blackbird's life on the ground. The very qualities that gave the JP-7 its thermal defiance at Mach 3.2, its extreme chemical stability and high flash point, made it a logistical paradox when motionless. While airborne, it was a sleek, invisible dart of speed. On the ground, it was a slow, deliberate liability. The constant slow leakage of JP-7 from the airframe's deliberately unsealed panels, a calculated design feature to allow for thermal expansion, meant the aircraft was most vulnerable when it was stationary, bleeding its volatile, precious lifeblood onto the tarmac. This necessitated the critical high-tempo maneuver of the hot refueling, where the aircraft was serviced and prepared for an immediate relaunch after a mission. The machine could not linger, could not sit full of fuel, for the leakage was too great, too demanding on the supply chain. The machine was designed to run, to fly, to move, to be hot. It was most dangerous when it was a flying chemical reaction, always on the knife edge of thermal or structural failure, the fuel its volatile, necessary lifeblood. But when that reaction slowed to a halt, the leaks began, and the invulnerable Sentinel became a delicate, vulnerable piece of industrial art, dependent on the tireless, unseen efforts of the ground crews to keep its complex chemistry operational. The SR-71 was not an airplane in the conventional sense. It was a metaphor in motion, a stunning, unapologetic commitment to a technological ideal that traded all conventional simplicity for absolute, unchallengeable chemical speed. In the chill, fluorescent glow of a subterranean Soviet command bunker near the Baltic Sea, Major General Anatoly Volkov, head of a crucial air defense sector, stared at the radar screen, his face a mask of cold, analytical frustration. The blip was not a blip. It was an infuriatingly fast streak, a phantom signature moving at a velocity that mocked the very concept of deterrence. His hands, resting on the steel console, gripped a detailed report outlining the technical parameters of the American menace, the SR-71 Blackbird. It was a machine that existed not just outside their airspace, but outside the very mathematics of engagement. The problem was simple. While Volkov commanded thousands of men and the brute power of mass-produced SA-2 guideline, missiles, the American intelligence machine, had achieved something fundamentally different. This was the ultimate juxtaposition of ideologies. The Soviet Union built air power upon the principles of vast, overwhelming numbers, robust simplicity, and the standardization necessary for total war. Brute industrial power made manifest in squadrons of MiG fighters and acres of missile launchers, grounded in conventional materials and standard logistics. The Blackbird, by contrast, was a high-cost, hyper-specialized technical solution, a bespoke expression of engineering luxury built of expensive titanium and fueled by a uniquely refined chemical elixir. It was a single, sleek, unapologetic repudiation of the Soviet military philosophy. They poured millions of rubles into saturation defense. The Americans poured billions into making one aircraft unreachable. The technical deep dive into the problem proved its rhetorical futility. The impossibility of the intercept was not a matter of poor marksmanship or malfunctioning equipment. It was a non-negotiable consequence of physics. At the Blackbird's cruising speed of Mach 3.2, the aircraft reduced the reaction time of Volkov's air defenses from minutes to a terrifying few seconds. By the time the early warning radar acquired the target acquisition radar locked, and the launch sequence was initiated, the Blackbird was often already beyond the effective range. The cone of theoretical possibility for a successful intercept, the narrow, vanishing space where the missile could actually overtake its quarry, was constantly shrinking with every passing mile, a cruel, mocking function of differential velocity. The SR-71 simply traveled faster than the information needed to destroy it. Initially, within the cynical camaraderie of the Soviet High Command, there may have been derision for the odd black shape that leaked fuel and required a dedicated chemical refinery to fly. But that derision quickly curdled into cold, hard tension and analytical terror upon realizing its sheer invincibility. It was not a joke, it was a constant overhead insult to Soviet territorial integrity and military capability. And the numbers told the true story of this operational futility, providing the ultimate statistical reveal. Over its decades of service, the American Blackbird was targeted by 0 successful intercepts. The missile count against the aircraft was known to be in the hundreds, yet the score remained 0 to nothing. The cost difference was staggering. The price of a single, highly specialized JP-7 guzzling Blackbird with its bespoke titanium airframe was astronomical. But the cost to the adversary, the Soviet Union, was the operational futility of firing thousands of pounds of sophisticated guidance equipment and warhead material, expensive, mass-produced weapons, into empty air, all because one single American machine existed in a realm of speed, chemistry, and logistics they could not match. The American machine was a costly deterrent, yes, but the cost to the adversary was the relentless, undeniable mathematics of defeat. The interior of the SR-71 at Mach 3.2 was not merely a pressurized cabin. It was an environment fundamentally alien to the human element, a testament to the fact that the ultimate speed demanded total separation from the warm, forgiving world below. A slow-burn, deep dive into the sensory experience reveals an atmosphere of carefully managed hostility. Despite the air conditioning systems fighting a losing battle against the thermal soak, the cockpit remained notoriously hot, forcing the reconnaissance systems officer and the pilot to strap themselves into pressurized, full-body flight suits that were less uniform and more personal spacecraft, designed to protect them should the cabin suddenly decompress at 93,000 feet, or should the structural shell fail under the agonizing heat load. The very air they breathed was filtered and recycled, carrying the subtle chemical odor that defined the machine. The lingering, slightly sweet scent of the specialized JP-7 fuel mingled with the sharp acidic trace of the ignition fluid, tetraethylborane. It was the smell of speed and solvents, a constant olfactory reminder that they were not merely flying an aircraft, but riding a contained, ongoing chemical reaction. This sensory reality extended outward, defining the machine's relationship with the ground. The most trivial, yet most significant detail of the Blackbird's existence was its infamous leakage. Upon landing, as the titanium airframe began the long, slow process of cooling from its 800-degree Fahrenheit cruising temperature, the specialized JP-7 fuel would begin to weep from the seams. This was not a mechanical flaw to be fixed, but a calculated risk, a necessary feature inherent in a machine whose structural panels were designed to fit loosely on the ground to accommodate the massive thermal expansion at speed. On the tarmac, the volatile, clear fluid did not just leak, it bled from the aircraft, forming viscous puddles beneath the engines and wings, an oily, pungent sweat announcing its readiness for the next high-Mach run. This leakage, this simple, constant drip, was the physical, liquid manifestation of the high-stakes design philosophy. The aircraft was intentionally structurally imperfect when motionless. Standing in sharp contrast to the helmeted, rarefied isolation of the pilots were the ground crew, the anonymous figures operating in the humid chemical environment below. These were the true rhetorical foils of the operation. Clad in specialized protective gear, working in shifts under constant pressure, they were the indispensable cogs in the logistical machine, routinely handling the very fuel that demanded such rigorous protocols. They were tasked with maintaining a machine that was supposed to leak, to perform the messy manual labor required to manage a vehicle that was only technically perfect at over 3 times the speed of sound. While the pilot and RSO were concerned with the horizon and the velocity vector, the ground crew dealt with the JP-7 at its most mundane and most chemically demanding, ensuring that the tetraethylborane was safely topped off and that the main tanks were full for the next hot refueling cycle. Their constant unseen battle with the dripping fuel, the acrid solvents, and the unforgiving thermal cycling underscored the Blackbird's fundamental truth. Its supremacy was not built solely on the brilliance of its designers or the daring of its crews, but upon the tireless industrial-scale management of exotic chemistry, a constant visceral struggle fought by the hands that wrestled with the heavy, pungent reality of a machine that was always slightly hostile to the world it occupied. The ultimate vindication of the SR-71 lay not in the pilot's cockpit, nor in the rarefied atmosphere of Mach 3, but in the sprawling, unseen network of chemical processing plants that spanned the American industrial heartland. This was the true theater of the Cold War's logistics, a technical and industrial supremacy narrative where the machine's invincibility was directly traceable to the relentless, specialized production of its fuel. The operational life of the mere 32 airframes produced was utterly dependent upon a complex, bespoke logistics chain, a pipeline of purity and precision that elevated the simple act of fuel delivery to a national strategic commitment. The very existence of the Blackbird was the most powerful rhetorical statement possible regarding industrial capacity, a tangible, flying assertion that the United States could afford to custom design the very petroleum product necessary to achieve a narrow, unchallengeable technological advantage. The statistical reveal of this sustainment effort was staggering, a volume of expenditure that dwarfed the operational budgets of many nations. Over its decades of service, the amount of hyper-refined JP-7 fuel produced and consumed reached a total figure equivalent to the entire fuel consumption of many smaller nations' air forces, a flow of specialized petroleum dedicated to sustaining one tiny elite reconnaissance fleet. This immense throughput underscored the fact that the supply chain was not merely robust, it was a bespoke industrial endeavor, a parallel system of refining and distribution that existed solely to service the chemical demands of a handful of titanium aircraft. The cost of manufacturing this specialized fluid, stripped of volatile components and fortified with specialized additives to resist coking and boiling, was orders of magnitude greater than conventional jet fuel, demanding a commitment of resources that only the American economy could bear without flinching. This commitment provided the perfect unapologetic contrast to the Soviet system. The AHT Soviet equivalent, their high-speed aircraft, were constrained by the necessity of utilizing mass-produced petroleum products, fuels designed to be interchangeable, easily produced in volume, and compatible with common battlefield logistics. Their strategic decisions were therefore constrained by the common denominator of their chemical supply. The Blackbird, conversely, was the ultimate expression of technical luxury, its requirements dictated purely by the physics of extreme speed, and its needs met by a powerful, specialized refining industry able to custom print its chemical requirements. The Blackbird's speed was thus not a single engineering feat, but a manifestation of unlimited resources applied specifically to the chemical and refining industries, turning economic power into military utility. The cost per hour was ruinous, the logistical chain complex to the point of absurdity, yet it was sustained relentlessly for decades. This reality formed the unwavering data-supported conclusion of the Blackbird's operational record. The relatively low number of airframes built, the astronomical cost per operational hour, and the absolute invulnerability of the machine were all interwoven, inextricable facts. The Blackbird could only maintain its unchallengeable position because the United States could afford to custom print its own fuel for a tiny elite fleet. It was a projection of economic power as much as military power, a loud, silent testament that the nation was willing to dedicate a massive, specialized percentage of its chemical and petroleum industrial output, not to the masses, but to a few select machines capable of bending the laws of physics. The sustainment pipeline, thick with the expensive, hyper-pure, specialized hydrocarbon, was the invisible, continuous thread of gold that made the Blackbird's invincibility a tangible, enduring fact of the Cold War. The mathematics of its sustainment proved that in the realm of technological warfare, superior logistics and specialized chemistry could be a more decisive factor than mere numbers of airframes or missiles. The clock read precisely 0727 hours on March 6, 1990, the date indelibly marked as the last operational surge of the SR-71 Blackbird. This final record-breaking flight, a sprint from the shores of California across the continental expanse to Dulles, Virginia, was the machine's definitive, dramatic curtain call, a spectacular, self-imposed climax to decades of unmatched performance. Pilot Ed Yalding and Reconnaissance Systems Officer J.T. Vida strapped themselves into their pressurized suits, preparing not for a mission of stealth, but for a public, visceral demonstration of a technical ambition that would never again be fully realized. This was the moment the pacing accelerated dramatically, pushing the aging titanium relic to its absolute thermal and structural limits, transforming the farewell into an awe-inspiring, somber tribute to an era of unrestrained technical spending. As they cleared the coast, the afterburners ignited with a controlled, deafening thunder, and the Blackbird surged into its domain of Mach 3.3. The sheer physical violence of the acceleration, the profound knowledge of being strapped to a screaming locomotive that existed only to defy friction, was the crew's final shared experience of the machine's power. Outside, the air was being physically tortured by the speed, compressing and heating against the nose and wings until the external skin temperature of the titanium structure stabilized above 850 degrees Fahrenheit, a glow of contained violence that defined the aircraft's purpose. Inside, the thermal soak was relentless, the heat a constant, pervasive reminder that they were operating at the knife edge of material failure. The undisputed climax of this flight was the ultimate, visceral proof of the original thesis. The speed was a chemical product, its existence predicated entirely on the logistical commitment to the JP-7 fuel. The Blackbird did not survive this punishing thermal assault through the strength of its titanium alone. It survived because the hyper-refined JP-7 was relentlessly circulating through its structure, acting not as a mere propellant, but as the essential internal coolant, absorbing the ferocious kinetic heat that would have instantly melted any conventional aircraft. Without the specific exotic properties of that fuel, without its unwavering reluctance to vaporize or ignite under the extreme temperatures, the delicate hydraulic lines would have boiled, the titanium panels would have warped catastrophically, and the world's fastest air-breathing machine would have simply torn itself apart in a blistering high-altitude catastrophe. The Mach 3 sprint was the final unchallengeable demonstration that the genius of the airframe was entirely secondary to the genius of its bespoke, circulating chemistry. Yet, in the final profound ironic conclusion, this spectacular machine was ultimately grounded not by a Soviet missile, not by a mechanical structural failure induced by a catastrophic thermal gradient, but by a simple, indifferent act of budgetary calculus. The prohibitive cost of sustaining its bespoke logistics chain, the specific, specialized infrastructure required to constantly produce, refine, store, and transport the unique JP-7 fuel and its volatile tetraethylborane ignition agent became the single, non-negotiable factor in its retirement. The Blackbird was not defeated by its enemies, but by the overwhelming, quiet mathematics of sustainment. The final descent into Dulles, breaking the transcontinental speed record and culminating in a perfect subsonic landing, was an act of both triumph and profound defeat. The American industrial machine had proven it could build the impossible, but in the end, it decided it could no longer afford the chemistry required to keep the impossible flying. The machine, a testament to an era of unrestrained technical ambition, was forever silenced not by war, but by the bottom line of the Treasury, a costly, leaking giant grounded by the very expense of its own chemical lifeblood. The final grounding of the fleet was not an act of surrender to an adversary, but a stark, data-supported conclusion drawn from the cold, hard balance sheets of the post-Cold War world. When the last of the operational SR-71 Blackbirds were retired and shunted to the silent sanctity of museums, the entire complex JP-7 supply chain, that bespoke industrial marvel, was simultaneously dismantled and retired. A clear signal that the era of unrestrained technical ambition had drawn to a close. The machine's legendary invincibility, its decades of untouchable surveillance at Mach 3, was ultimately predicated upon a chemical formula and a corresponding industrial effort that had become simply too specialized, too demanding, and too prohibitively expensive to maintain indefinitely. The decision was not a failure of engineering, but a logistical inevitability, proving that even the most spectacular display of speed could not outrun the dictates of long-term economic sustainment. The Blackbird's legacy, therefore, is not purely one of aerodynamic prowess. It stands as the ultimate rhetorical final statement on American industrial and chemical capability during the Cold War. It was the physical manifestation of a singular, profound willingness to invent an entirely new, bespoke logistics chain, a specific chemical ecosystem for the sole purpose of achieving a single, unchallengeable technical edge. The fact that an aircraft's operational life required its own dedicated, limited-run product line within the vast global petroleum market remains the clearest testament to the era's commitment to technical supremacy at any cost. This commitment to the uncommon and the complex was, in itself, a decisive weapon. The lasting significance of this entire narrative is best captured in a final juxtaposition of scales, a poignant contrast between the immense and the minute. On one side stood the astronomical cost and complexity, the billions of dollars, the decades of specialized refining, and the massive invisible volumes of custom-made JP-7 hydrocarbon required to feed those 32 airframes. On the other side stood a simple ground-level observation, the easily understood image of that exact fuel, a clear, volatile weep from the unsealed titanium panels, landing on a warm tarmac and melting the asphalt under the tires of the incredible machine. The grand technical narrative of speed, heat, and space was reduced to a mundane interaction between two petroleum products, one dissolving the other. This seemingly trivial detail of the melted asphalt becomes cosmically significant. It was the most visible, ground-level proof that the Blackbird operated in a realm of thermal and chemical reality utterly separate from the common world beneath its wheels. That dissolving tarmac was the boundary marker, the physical line separating conventional flight from the unrestrained ambition of Mach 3. The aircraft was powered by a volatile secret written not in the blueprints of its wings, but in the exacting proprietary language of hydrocarbon refinement and engineering excellence. It is an incontestable fact of military history that the Blackbird's speed was its shield, and the JP-7 was the invisible, complicated, and utterly essential engine of that technical supremacy. The Blackbird may be permanently grounded, but the chemical truth of its invincibility endures.